control unit. The two modules. There's the control unit FSM, and there's the control unit. There's a reset of them to FSM. And because both of these modules have this 630 of the instruction has been right here, IRC for instruction 630. These 7 bits go into the sound. Same 7 bits go into the further. Those 7 bits. Right, that's the output. Okay. Also, these 3 bits, the 14 through 12, go into both FSM and the code. What are those 3 bits? Function 3, the function 3. Okay. We see both the output and the function 3 that they're going into both function. Now the decoder also has a single 30th bit going. We'll talk about a lot in next class. What is, oh, and also the decoder has output of your branch condition generator going. Remember the 3 outputs that we use in 3 comparisons. Because even though we have 6 really branches, we use 3 comparisons. But notice that we go into this decoder. Look at the outputs of the FSM. What are these outputs mainly? The ones in black. Good. Yeah, enabled, right? Enabled the unit. Reset. Now, in red, the reason I put these out is because these outputs have to do with interrupts. And like I've mentioned a few times in class, to the time we lost it all the way in the storm, we're not going to be able to keep interrupts, unfortunately. So you don't need those out, but you can just neglect it. There's also a tier override is the decoder module. Yeah, you're not going to need that. So look at the output of the decoder. Where do these outputs connect? ALU1, ALU2, ALU13, or are right select. Yeah, those all go to the muxes. Okay, so the output of the decoder is controlling the select of all of the muxes, and then the FSM is controlling when and reads and writes happen. Okay, so remember, this is from your CPU that they're synchronous. And on a clock, there's sequential, they have memory. Sequential. Just talk about mode outputs. Read write enabled. And the thing about the FSM is that it's time critical. And these reads and writes have to occur at a certain time. And what I mean by time critical, read, writes, have to occur at certain times. Okay, so I'm going to see you at sound. You probably get a decoder. It's asynchronous. Combinational, right? Memory. All the outputs are not selected, not selects. And so all outputs. Not selects. And so not selects that route the data. Right? Because remember how Fox works with the select input of a box, it chooses which of the multiple inputs make the output. Right? So you see that's how we're routing the data through the processes through the control decoder output. And then the FSM is controlling when the read and the write happen. Now, the decoder, it's not time critical. As long as data flows out every cycle. The ALU media generator, branch address generator, instruction calls for that, etc. You can also advances the program counter next instruction address. In one class. About this before the ALU, right? Remember how we said we want the ALU to be very efficient, right? Not to have any on propagation delay. So that's why we use one case statement. One case statement give us 1 month. As opposed to the different case statements, to get chain, long chain of circuitry, which is going to have one propagation delay. I mean, hopefully, when you did your ALU design, you looked at the elaborate design schematic that Vado actually synthesized, right? Made sure it's just a single month. Okay, but if you want to be really complicated for your ALU, chances are it's not going to work unless you put everything up. Okay, because you probably your ALU, it's not going to be able, this data is not going to be able to flow from the output of the memory module, your instruction all the way through and getting the results stored, also advancing the program counter to end instruction within one clock cycle. And I think I mentioned also, we'll talk about it more coming up, but in previous classes, I talked about how those instructions take 2 clock cycles to be processed. One clock cycle is to get the instruction. The second clock cycle is to execute the instruction. So that's what we're talking about here, the execution time. Execution time has to be 1 clock cycle because getting the instruction has to be 1 clock cycle. Now, that's most instructions. There's a few instructions, and we'll talk about this next week on Tuesday. There's a few instructions that take 3 clock cycles. Okay, but we're not going to talk about that today. We'll talk about that on Tuesday. Okay. All right. So, any questions on what we've done thus far? Let's get some basic information over those modules. Everybody good? So it says brief flights have to occur at certain times for time critical. How do you usually determine that they're good? The example is when we write, they were writing a result to a reg file register. Well, we don't want that to happen until the result is ready. Right? So that's what we mean by time critical. This write enable to put our result into the reg file register. Well, it can't happen until you have an answer, right? Until it's gone through the ALU. That's what's meant by time critical. So that's the example. All right. Well, in your CP 133 class, I'm sure you talked about FSM, and I'm sure you talked about state diagram, right? Because anytime you go to design an FSM, that's where you start. You always start with a state diagram. So here's the state diagram, not complete diagram, but arrows. But this is how many states we have. We have an initial state, init is short for initial. We'll have a fetch state. You can see why this is called fetch from now. And we'll have an execute state, abbreviated EX. Okay. Now you can see there's this arrow that goes into the initial state. That represents an external reset. Okay, created RS that is this reset right here. So what I mean by external, that eventually this external reset will connect to a button on your basis. Okay. Don't confuse this external reset with this reset. They're not the same. This reset is an output of our FSM. And I think a better way, I would recommend that we design almost reset like this on the water diagram. I would call this PC. Okay, but that's what it's for. It's to reset the program count. Okay? And in fact, that's what happens in our initial state. Okay? In our initial state, we want PC reset. Okay, and if you remember when you designed the program counter, you made the reset active high. Okay, so we want to make this active high. So once this is active high, because it's synchronous, on at the time of the rising edge of the clock, this high, that's going to make the program counter output go to 0. And what do we have at the output of the program counter? What is the program counter providing us? Is it the instruction? The address of the instruction. Right? The address of the instruction PSP, that's the output of the PC, our program counter. So why do we want to initially make the output of that program counter, which has the address of the instruction PSP? Why do we want to start initially with that at 0? For the first address to be executed at 0, 0, 0, 0. Well, the first instruction to be executed is at address 0, 0, 0. Yeah. See, the program always starts at address 0. Okay, so you see the reason why we reset the program counter to 0 initially is because that's where the first instruction is. First instruction of program at address all 0. Yeah, that makes sense. Okay, so then you go from the initial state to the fetch state, and as the name implies, you're getting something, okay, you're fetching it, and what you're fetching here is the instruction. So this is where you get the instruction. The instruction to be executed. And what would we have to enable in order for this to happen? One of these here. One of these is the input to the memory module. Right? Remember our code segment that has the instructions in the memory module, right? Our address coming from the program counter goes to our memory module. And then the out one of our memory module, that's where the instruction is going to be when one of these is enabled. Yeah, we didn't even want that information alone. You see in this state, one and we didn't make we made it action high. So when this is the one at the time of the next 0 to 1 transition of the clock, the instruction at our program counter address, which starting out is going to be address 0, that first instruction will now be at the output of D out 1. You have pushing point. Okay, so that's what's happening in the fetch state. It's getting the instruction and putting it at D out 1 of the memory module. Now what's got to happen is we got to execute that instruction. We have to make it happen. Right, and that's the one clock cycle we were talking about. That the data is going to flow from that T out 1 where the instruction is through the reg file, through the ALU, that's part of the instruction, or through the immediate generator, branch, and so on. Come back and advance the program counter. That all has to happen within one clock cycle. And it's all when we execute. So this is where we make instruction happen? How do we make it happen? We control the reading rights, but the output to that right now. We control the selects of the muxes that route the data to the output of the code. Right? Depending on what instruction we're executing, it's going to determine what these have to equal. How do you determine what these have to equal? Well, you got to draw out the data path and those things for each instruction. So you see how what we talked about earlier, right? Okay. Now, once an instruction's been executed, you go back and you get the next instruction. So you go back to fetch. Right? And you're just going to go back and forth between fetch and execute until you've executed the program. Okay, so if you were in my CP 133 class, you did much more complicated state diagrams than this. In my class, I had to do that sequence detector, which can be a little tricky. Then you also do a 4-bit multiplier, which isn't that much more than this. It's more stuff, but still not a very complicated state diagram. Now, what you're going to find code-wise, quite a bit of coding in the execution step. Okay, not much in fetch, not hardly any initial. But yeah, this is where you're going to be spending your time for hardware 6, also hardware 7. Okay, or yeah, that's some goes. Now, in addition, just to give you a little heads up, this is the state diagram for instructions that only need 2 clock cycles. On Tuesday, we'll talk about some instructions that need 3 clock cycles. And for those instructions, we're going to have to come back to this and edit it. Okay? We're going to have to add a state. Okay? But we'll do that on Tuesday. This state diagram is fine for hardware 6. So these 6 instructions that are in the sample program that the whole hardware 6, you can get your auditor to run this sample program. So get your auditor to do these 6 instructions. And all these 6 instructions only require 2 clock cycles. Okay, but your final project, where now you're going to have your auditor be able to execute all of the real instructions. So 30 some odd. So some of those have or need 3 clock cycles and require 3 states. So for hardware or for the final project, you're going to have a slightly different state diagram that again we'll talk about next week. Okay. Okay, so here I just repeated things that I said. I just wanted to have it written down. You should expect everything that I said. But key points again. The fact that the data is going to progress through 1 clock cycle. Again, that's the reason for an efficient pumps. And that's why again, you need 1 case statement. Efficient ALU. Efficient ALU where you use 1 case statement for 1 pump. Sorry about ALU for 1 case statement. And the other thing here then, just to stress. State in order to code it, that's the reason why you need the data path control signals. For every instruction, every real instruction. Okay, now, again, for hardware 6, because you're only running the sample program with 6 instructions, you just need the hardware 6 diagrams. It's truly done. And the others are very similar to what we've done. Okay, but for the final project, that's when you need the diagrams for all the real instructions. But again, you're going to see that there's a group of instructions that basically have all the same data and control. Just one difference, another group. So you start to see that. Not as much as doing 37 separate diagrams. You could do one diagram and then say, oh, the only thing that's different is these instructions with this one thing, kind of list, so one diagram, like maybe it's for 10 instructions. Okay, but there's still quite a few diagrams. So is it kind of like you're choosing in the FSM, you're like figuring out which instruction it is and then running a certain state diagram for each one? No, there's just this one state diagram, but in this execute state, based on what instruction you have, is going to determine which output gets what value. And then in the decoder, it's the same thing, except the output. But in the decoder, you're going to have some sort of case statement that based on the instruction makes these the values that have to be for that instruction to happen. So you're going to see that you're going to see that part of the code that you have to do for FSM is going to be very similar to the code that you're going to do for code. And you'll see that coming up. I'm going to outline how to do the code. It involves case statements. Yeah, you can have an if statement for a group of instructions too that I'll talk about. Okay, but before I start outlining, the system we're alive. Is everybody okay up to this point? You get a general idea what's going on and like the thinking behind it. Did this activity help? This right? You get some minds of the instructions of doing. Was there a question? No. Okay, so let's move on. Now let me get my actual code. I try to do a lot of my code. I make all kinds of errors, and even with my code, sometimes I make errors. So watch what I'm doing. If I make a syntax error or something I know about, let me know. All right. So first, let's talk about how you're going to model the FSM, the control unit FSM. So, white ball module. You start out with the module name. Now, again, be descriptive with your names. Like, see what I did here is I put C for control unit before FSM, and I tended to do that for all my modules, right? If I had like a reg file, I call it like RF, I use RF for an acronym. Do that for your inputs and outputs too. Because again, if you call all your inputs the same and all your outputs the same, and when you go to connect up all your lower level modules together, like in the top module, because that's another thing you got to do for hardware 6. And you just use like T1, T2, T3 instead of being descriptive. When you have to debug this, and you will have to debug it, there's no way around it. Okay? You will have to find problems. It's not going to work the first time, guaranteed. Well, if you've got like everything named the same, you're going to go bonkers trying to figure out on your timing diagram what's what signal is what. If you've got things nice and descriptive, you can say, oh, that's the output of my program counter. Oh, that's the output of this. Oh, that's where these two things connect. Okay, so it would save you in the long term if you just take a little extra time and be descriptive with the name. Okay, so the next thing after you have your module name, you'll declare your inputs and outputs, right? So you can see here you've got several inputs, half a dozen outputs or so. Then you're going to do this. Now, depending on who you had for CP, what instruction you had, you might have seen this before. When I taught CP 133 this past fall, I started to do this, but prior to last fall, I did it the way where you define the states in your FSM with binary numbers. Like you would say the state is binary 0 and binary. I see some people checking their head, so it needs to see it that way. This is much more convenient. See, what we're doing here is we're defining a type that's abbreviated ENUM, which is short for enumerate. Okay, and all enumerate means here is that instead of putting binary numbers to identify state, we're using labels. Okay, and you see I'm being descriptive, right? State initial, state fetch, state execute. Right, you put states here. That's what defines it as the state. And you see what's nice about this is a couple of things. One is, again, it's very descriptive. So when you have this on your timing diagram, you can look and say, oh, this is happening during an execute. Oh, this is happening during a fetch. Oh, this is happening during the initial state. As opposed to these were binary numbers, you would look and you go, oh, what 1-0? Oh, let's look, oh, 1-0. You know, it's just a lot more readable and nicer to have. You know, another reason it's good to do this method is if you have to go and edit your FSM, the beginning you go at the hardware fix, the final part you're going to add that third statement. But when you go to edit, if you don't have the enumeration, if you have the binary numbers, you've got to go in there and edit those binary numbers that represent the states because they couldn't change the order. Where if you use this, the software will do it for you. Right? So if you go in, you have to make edits and it changes where you know the order of these states, the software will automatically assign the right binary number. You don't have to think about it. Right? So it's just much nicer to do this. So if you learn how to do the binary numbers, you just want to stay with that. You know, I'm not gonna argue with you, but this is so much nicer. I really recommend you do this. Okay. All right, so after you have this definition, then you have to define your next state, your present state, just like you would you did this. Okay. Now comes for the register part of the FSM. So since it's a register, what kind of block am I going to use in my system Verilog or well, system Verilog? Always that one. So make sure I get that syntax right here. So it's always underscore FL. And then you have to tell it whether it's positive or zero, or you can positive. If you have go on to the rest of the modules. You have your inbound somewhere. Okay, so it's in this block, okay, the FF block, where we take care of this external reset. Okay, so we'll put an if statement. So if I call it CU underscore reset and be more descriptive of this reset. Okay, so when that's equal to 1, we're going to make present state. Now, what kind of assignment am I going to use? Since I'm going to always have that block. Is it the one with just the equal or the one with the arrow? I forget what that's blocking. I just remember arrow. Sign. So we would just assign, well, what would be assigned for present state if we're reset? What am I going to put next? This is state initial, right? Yeah, it's right here, right? When reset's active, it's going to go to the initial state. So this will be state IN or INI. Oh, there's a semicolon here. Okay, else. If we're not resetting the initial state, then what do we want to have happen? Yeah, present state will be assigned next state. Right, that's when it's going to use the decoder, right, to determine where the next state is. Okay, so this right here, this is all you ever need in the state register. Okay, this is going to be the same for hardware 6 in your final product. You don't change this. This is what it is. Okay, what's going to change between hardware 6 and your final project is what's in the state decoder, along with what's in the control in the decoder. That will okay, but this one just stays the same. Okay, that takes care of your reset. All right, so now we're going to do the code, the Verilog, or the state decoder. So a state decoder or any decoder, what kind of logic circuit is that? Combinational. So what kind of block are we going to use in system Verilog? Right, so I'll always underscore phone. And then again, and somewhere down here, somewhere at the end, somewhere, right? You always have to end of the time. Now, this is an outline. I'm not going to put everything up to it, but so you'll have to fill in the space. But what I would do next, and some people do it this way, and some people do it a different way. But what I like to do next is I set all my outputs to 0. All the outputs that I have sent to 0. So I would take PC write. I call it CU. Right? Just make that equal to 0. And then just do that for all the other outputs. Your read write, all of them. Just assign them to 0. Okay, now, what some people do is that instead of doing it this way, when they get to the case statement, okay, the next thing is going to be a case statement. Well, within the case statement, they'll put the value of all the outputs. But you see, if you do it this way, if you set all your outputs to 0 first, well, then in the case statement, you only have to write the output that's changing to a 1. Right? If you don't initialize your outputs to 0 first, well, you would have to list all the outputs, not only the one that is going to equal 1, but you have to put all the other ones to 0. Otherwise, your file is not going to like it. It'll come back with errors. Right? So I just think it's a little neater, code-wise, doing it that way. But yeah, it's up to you whether you want to do it that way or not. Okay, but the next thing that we would have is the case statement. And what would our case statement be sensitive to? What would we put in these parentheses? Not the output. What is the case statement that FSM going to decide? Right, what state we're going to, right? So remember, whatever we put in the parentheses, when that changes, that's when the case gets evaluated. So present state, right? If you present state, right? Because when present state gets updated, now it's going to come here and it's going to evaluate whatever we put. Okay, because remember, your FSM in your data code part, this is where you put, where the FSM is going to go next in its state diagram, right? Along with what the values have to be in that state. So, like the first thing in our case statement here, we would take care of the initial state. The state of it. And we have an N down here somewhere. So, here's where we put what we want to happen in that state. And also, here's where we put, where the next state is at. So, what do we want to happen in this state? Yeah, right there. PC reset equal 1. PC score reset equal to 1. Tick mark 1, tick mark 2. 1. And then what do we want? Where do we want it to go from the initial state? When I go into the next state. So then you have next state equals that state underscore fetch. That's what this is. Yeah, I see that the PC reset, that's an output. And if you look on the diagram, that goes to the program. So that's how that would be compared. Yeah, that just showed up that. The output of the controller is controlling another module, right? It's controlling the PC. Okay. All right, so that's what you would have for your state initial, and you have to have your fetch state. So another state fetch. and they have an end somewhere. Right now, I'm not going to write it, but just like here, you put what you want to happen in that state. So we want the memory able to go on, and then you put what the next state is going to, which we're going from fetch to where to execute. So then you have your execute state. State executes. Now, what we want to happen in the execute state depends on the instruction. Right? Because depending on the instruction, it's going to determine what we want to do. And how do we tell like what instruction we have? Yeah, opcode determines the type of instruction. Now, for these 6 instructions that we have, what has to happen for each type of instruction or what is the same. So for hardware 6, your case statement for the cover part of your FSM, it can just be one case statement that depends on the octave. But you can just put so you can just put, like case octave, right? And then you'll have an option, like say 7, take part B. I don't know. Let's say we have an octave like this. Right, so with that instruction, with that opcode, you would then put between the beginning and the end, you would put, with these outputs have to be a 1. Okay, and then you have another option, right? You have another opcode in the beginning and end, and for that instruction, you just put what the output to the FSM have to be for that instruction. Okay, so like I said, for hardware 6, which you just run those 6 instructions, a single case statement will be fine for your FSM part of the code. But you'll see that for the final project, you're going to have to come back to this, and you're going to have to either use nested case statement or if statements for that case. Okay, so we'll talk more about that next week. For hardware 6, for your decoder part, you may have to do nested cases, and I'll give you an example of that. You're talking about one case statement within the execute state. Yes. Yeah. Yeah, there's no case statement in these other states. Because in these other states, we just want the same thing to happen. Okay, but when you get to the execute state, right, because of instruction, have different requirements or need different requirements. That's why you need the case statement. Depending on the instruction, these elements can be different. Does that make sense? All right, so again, I left out things, but my goal wasn't to give you everything. My goal was just to kind of give you the approach, so you can get started. Okay, I'm sure there's mistakes there. I probably should have some calls and stuff like that. My opinion wasn't make it perfect. Okay. All right. So that's the control unit FSM. You'll also have to do the control unit decoder. Now, the control unit decoder is a lot like the decoder of the FSM as far as how you set it up. And I'm just doing an outline here. But then, you always start out with logic like this store decoder. You clear your inputs and outputs. So, you get like 5 outputs and I don't know, about 5 or 6 inputs there. So what kind of circuit is the decoder again? Or a decoder? Combination also, you're going to use what kind of block? Always. Now, again, what I like to do is to initialize all the elements to 0. And so, for example, CU underscore ALU underscore 1 with 0. Actually, it's a 4-bit. Okay, then you do all the other ones. Okay. Then you're going to have a case field. You're going to assign your outputs. And the outputs of that control unit code based on the opcode. So this is where you have a statement that opcode is the sensitive variable. Okay, so again, you'll have like an option. If this might be your U type option. Okay, and for your U type option, for our sample program, we only have in fact, if you look at the instruction set, there's only 2 U type instructions. There's the LUI and then there's the A or something. You haven't talked about that much yet. And those 2 U type instructions have different opcodes. Like this one has an opcode say about 37 hex, but the other U type instructions have an opcode of like 67 or something like that. Okay, so for this type of instruction, right, you're just going to have a one option for it. Okay. But then when you get to say the you've got 2 R type instructions. So if you just have the opcode, like have the same so yeah, so both of these have the same opcode. So how can we differentiate? They have the same opcode. The function 3, right? So they have different function 3 different types. SLT XOR, XLT 010, XOR 100. So you see that's why we need a case within a case. Right? We have a case that's sensitive to the opcode, but then we have a case sensitive to function 3. And so see this case is going to be within this case. Right? This case gets into the instruction just that opcode. But then if you have more than one instruction with the same opcode, now you get a look at the function 3 that's the determination. Okay? That's what's meant by a case within a case. But you can also have an if statement. And where the if statement may come in handy is when you get to your branch instruction. Okay, so there's 3 comparisons that are being done, but we have 6 branch instructions now. 6 total. You don't have to worry about all 6 right now. You just got to worry about this one here. Right, but you still might be in if statement because if it's true, you want this to happen. If it's not true, you want something else to happen. And that's likely to mean that these are different. And in fact, the pieces are different, right? If you're branching, that's a 2. If you're not branching, that's a 0. Okay. So can you see how the control unit decoder is set up similar to the state decoder, right? The decoder part of the FSM is very similar as far as their setup. Right. Now, the only other thing, and I'll let you go ahead and get started on your assignments. The other thing you'll need for hardware 6, in addition to those 2 modules, right? The control unit FSM and the control unit. The other thing you'll need is you'll need the top module that connects all these lower level modules together. Make sure you're finally at the point where you can connect these all up. So when you do that top module, I recommend following this organization. Yes, hardware 6. Hardware 6 is doing the FSM, the decoder, so it can execute this program that has 6 instructions. And yeah, in order to do that, you have to have your auto output together. So just like any top module, you have to declare your main input to your main output. See, here's a high level black box diagram of the auto. So you basically have to set your clock, your idle button, and just reset again. Interrupt is incorrect because we're not going to interrupt. So I want to either put, anything I have in red for different outputs, don't even bother because we're not going to, don't even have to declare it. So, when you do that auto module, your hot module, you'll have 3 main inputs, 3 main outputs. Okay. But then, like any hot level module, you have to design, you have to declare your internal signals, right? Those are the connection points. So everywhere there's a connection on that diagram, there's a do. Right? Everywhere there's a connection between lower level modules, you have to declare a signal. And again, make them restricted. Don't use like P1, P2, P3. Maybe have like PC out underscore ADR1 or something. Something that identifies what is connected. Right? When you're troubleshooting, you just look and say, oh, that's this connection. Oh, that's this. Instead of T1, where the heck is that? T3, where the heck is that? Yep. Yes. Right, yeah, yeah. This module right here, CSR, that stands for control status register, that's for interrupts. So yeah, this you don't even bother. So again, that's why you don't have enough time to fit. If I find interrupted, another lecture, another assignment, all of those final product. Right? You just don't have enough time. I'm sorry for that because for senior students especially, eventually you get to know interrupts. Dr. Hummel, he knows about this. He teaches the class, that follow alongs to this that he interrupts. He was like, don't worry, I always review interrupts at the beginning. He'll spend extra time. But again, it's just unfortunate the way things worked out with losing the 2 classes. So I think the other reason is that this 233 class, or was that like 330? It would be, well, I think this is the class that he teaches after this, I think is 333. So yeah, he would review this. I think he reviews more than interrupts. Like he'll review, I think the first week he said or something like that. So CSI. Yes, CSI it's not very better. One of those diagrams on the flip side has it without it. Let me see if I have it. I can make copies of it. Yeah, see. I have a diagram that the skills are. So if you want, I can make copies of this next time. Okay, I'll do that. I'll take 3. You'll take 3. Well, I'll make a bunch of copies. Actually, let me put this in my bag. I can't forget to find. I gotta try to remember that. Okay, I'll do both. Okay, so the only other thing here is again in the top module, after you define your internal signals, what I would recommend is put your case statements for the other muxes that you haven't done yet, because you've only done the mux for the program, right? That was part of like hardware number 2. So you have 3 other muxes, 2 muxes for the board at ELU, and you also have mux here in the file for the money data. And you can do that in the top module. You can just do 3 separate case statements. Okay, 1 for each mux. Now, another approach that some people do is building a file, So, yeah, we can do that way too. And then the last thing is the code that makes the connection be online. Okay. So once you have all this, okay, once you have the control unit module, you get the top module all linked together, well, then you go ahead and you do a simulation. Now, for hardware 6, you're not downloading anything to the basis for it. It's all simulation. Not until the final project where you have your auto working and it's running all the instructions. That's the time that you'll download the auto down to the basis for it. So for hardware 6, you're just checking that it's executing this program, sample program in the simulation. And there's a video that Dr. Hummel made, and I posted it on Canvas under meeting 11, which is the next meeting, where he showed you what you should see in that simulation. He showed you the timing diagram, and go through it, and showed you how to check to make sure that it's running the program correctly. So when you get ready to do the simulation for hardware 6, watch that video. It's about an hour-long video. However, in Canvas, I put where to start watching it, like the 26-minute mark, somewhere around there. And he shows you exactly what your simulation for hardware 6 should look like. Okay. Like I said, this isn't due for another 2 weeks because there's quite a bit to do. There's no way around it. But, like anything, there's good news, bad news, right? A little bit of work to do next week. But the good news is, if you have hardware 6 working, this is not going to change for the final product. But if your hardware 6 is working, your top module is good. Okay. What's going to change between hardware 6 and final project is the state decoder in your FSM and your control decoder, because when you add more instructions, this is going to require more, right? More of a case statement. Like I said, we probably have to test it. But the same thing here. When you add instructions, this is going to be more. We'll talk about next week why this 30th bit don't get the code. But we'll preview is that what you'll find out if you take a careful look at the instructions in the instruction manual is that there are pairs of instructions, that have the same code, they have the same function prefix. So for those pairs, what distinguishes them is the 30th bit. When the 30th bit is 0, it's one of those pairs. The 30th bit is 1, it's the other two. Okay, so that's also something you're going to have to account for in the code. If you don't have to worry about that, then go with the final process. Okay, Scrivener 60, you just got to worry about these 6 instructions. Any questions before we end it? We're taking the lecture part. We have Phil 6 to work on things. Okay. Well, like I said, priority should be the branch stuff, because that's due tomorrow, and then the software 5, because that's due Tuesday. And then this isn't due for 2 weeks, so the lower priority if you haven't done the others.